Welcome to ITT Industries' Little Red Schoolhouse, a fully equipped learning center that has graduated over 45,000 students since opening its doors in 1954. Graduates from every state in the Union and most countries on the planet. The subjects taught here vary greatly, but are designed to teach engineers, contractors, and installers about the proper design, installation, and maintenance of hydronic and steam systems. Hi, I'm Roy Algren, and today we're bringing the Little Red Schoolhouse to you. We hope to show you some things that will help you in understanding hydronic systems a little bit better. This is our pump compression tank location demonstrator. We use it to demonstrate the importance of the location of the pump in the compression tank, particularly if it's a high-headed pump. And here to take us through this important demonstration is Gil Summer, one of our schoolhouse instructors.
Thank you, Roy. Let me start out by saying all the pump does is circulate the fluid in the system. The point at which the tank is connected to the system is the point at which the tank exerts its pressure on the system. The pressure at that point cannot change unless the pressure in the tank changes. The pressure in the tank can only change if the proportions of water and air change. The pump cannot change the pressure in the tank because the pump cannot change the proportions of air and water in the tank. Consequently, pumping toward the tank or away from the tank will not change the pressure at that point, but there are some other ramifications. If the tank is connected closely to the pump suction, when the pump operates, all of the pump head will show up as an increase in pressure throughout the system. The head is used to overcome the piping resistance. The pressure then at every point in the system is higher with the pump running than it is with the pump off. However, if the tank is connected closely to the pump discharge, a strange thing occurs. The pump can't change the pressure at the discharge. Consequently, being a one-trick pony, all it can do is reduce the pressure at the suction. When the pump is in operation then, the pressure in the system is lower at every point than when it is with the pump not operating. If the head of the pump is greater than the non-operating pressure in the system, at least part of the piping system will operate in a vacuum. An automatic air vent installed in an area with a negative pressure will suck air into the system. Not a welcome occurrence. Since seeing is believing, hopefully the following demonstration will solidify your thinking on this problem. This is a 1522 pump with a head greater than the non-operating pressure of the piping system. It also has a closed piping system. The tank has a gauge which is connected to a manifold which enables us to connect the tank to the pump discharge or the pump suction. We have a large pressure gauge. We have a large compound gauge on the suction side. We have sight glasses which can be lighted, which will show us what happens as we change the location of that tank from the suction to the discharge. First, the tank is connected to the suction. With the pump not operating, all of the gauges read the same 12 psi. When the pump starts up, the pressure on the tank and the pump suction remain at 12 psi. The pressure at the pump discharge goes to 32 psi, which reflects the head of the pump, 20 psi or 46 feet. Importantly, both of the sight glasses remain clear. Now let's turn off the pump and change the location of the tank from the pump suction to the pump discharge. Again, with the pump off, all of the gauges read 12 psi. Once we start the pump, you'll notice that the pump discharge and the tank pressures remain at 12 psi, but the pump suction has dropped to 13 inches of mercury. The difference between the pump suction and pump discharge is equivalent to 46 feet the head of the pump. Note that the sight glasses are no longer clear. Air has come out of solution and the bubbles are easily seen. The amount of air that is soluble in water depends upon the temperature and pressure. Air is more soluble at higher pressure or lower temperature. This demonstration clearly shows the importance of locating the tank at the pump suction. To summarize, free air which can be caused by a drop in pressure can air bind circuits, can cause noise, can even cause cavitation. This demonstration clearly shows that simply hooking the tank up to the pump suction eliminates that drop in pressure, which prevents air coming out of solution, causing noise, causing cavitation. Here's hoping that this demonstration will prove beneficial to you in your future endeavors.
What are the problems you get with your heating systems? Isn't it that there's not enough heat or there's too much noise? To solve these problems, let's take a look at this boiler demonstrator. And here to take you through it is our schoolhouse instructor, Mick Gerhardt.
Thanks, Roy. What's the reasons for most of these complaints? More often than not, it's air. That's right, air. Can an air-bound radiator prevent us from getting the circulation of the heating fluid through the system? Of course it can. Also, won't air moving through our system cause noise? Yes. So naturally, the solution should be to remove air from the system. We'll use this boiler mock-up to demonstrate how and where we might remove air from our system. Our first question would be, what conditions help us eliminate air from the system? How about temperature, right? So let's look at where the temperature is the warmest. Here, the boiler. Remember, the higher the temperature, the less air is soluble in water. Another condition that would be helpful in eliminating air is the location where the water velocity is low. The slower the velocity of water, the more likely the entrained air will rise. And where does that occur? Again, right here in the boiler. Notice the top of our boiler. We have a device to help remove air from our boiler. This is an air troll boiler fitting. Let's take a look at how this boiler fitting is designed. The air troll boiler fitting is designed to allow air to rise up the boiler fitting and then be diverted to the air tank. Next, air travels through piping that is pitched up to the air troll tank fitting. There, it is allowed to pass into the compression tank. There is a small baffle that restricts the flow of water. This helps us prevent gravity circulation. If we didn't have this baffle there, the warm water would be able to freely rise directly from the boiler into the compression tank. Once in the compression tank, it would cool down to ambient temperature. As it cools down, it will absorb air. Also, as it cools down, it becomes more dense. And because it becomes more dense, it will counterflow back through this piping back into the boiler. Once in the boiler, it is allowed to be reheated and pumped through the system. Next, the water will circulate through the system. As it's circulating through the system, the water will be allowed to cool down. As the water cools down, air will come out of solution, and this will cause noise problems. Also, because air is coming out of solution, soon it's going to hit a part of the system where there is a low velocity. Most likely, that will be the radiator. Another feature of the air troll tank fitting is the vent valve. On initial fill of the system, usually too much air will be trapped in the compression tank. If we open the vent valve, the water level will rise in the tank, forcing the excess air out the vent valve, thus establishing a correct ratio of air to water in the tank. The air troll boiler fitting and tank fitting work together to maintain the proper level in the compression tank. Also notice that our makeup piping meets the piping that goes up to the compression tank. The reason for that is, as the cooler water comes into our system, the entrained air is allowed to rise up into the compression tank. Notice that all these components are designed to work together. After all, air has a vital role in maintaining our system. However, to be beneficial, it must be controlled. That's why we have called it air control for over 40 years. Another way to manage air is to eliminate it from the system, as can be done with with the B&G HydroFlow unit. Here we have many of the same similar components. They perform the same function in a different manner. To separate air, the airflow is equipped with an enhanced air separator. This air removal device removes air by using the principle of coalescence. Inside is a stainless steel brush which collects tiny air bubbles. As more water passes through, more air is collected on the fingers of the brush. When enough bubbles combine, the buoyant force of the larger bubbles is enough to cause the bubbles to rise to the top, where it can automatically be vented out of the system. To ensure it captures as much air as possible, we have added a diffuser. Instead of an expansion tank to control expansion, we now have a pressurized tank. This tank is not designed to accept air from the system. This particular tank is a bladder tank. On one side of the bladder, we have air that is pressurized to the system pressure. On the other side of the bladder, we have the system water. As our system heats up, the water expands into the tank as before. However, now there is no contact between the system and the air. This design allows us to use a smaller tank for our system. What we have seen here is that there are a number of ways to separate air from water in a hydronic system. There are also different types of tanks to provide pressure and accept thermal expansion. The important point to remember is that every hydronic system needs to have the proper air management and pressurization equipment installed.
This is our primary-secondary pumping demonstrator, designed to show how primary-secondary pumping actually works. To begin with, two pumping circuits can be isolated in the sense that pumping effects in one circuit will have no effect on flow in the other. Remember that the key point is to have low pressure drop in the piece of pipe that's common to both circuits. Here we have a primary circuit. Starting at the boiler, we see the compression tank connection, a primary pump, a supply pipe going out to the system, and a return pipe coming back from the system. A crossover bridge that connects between the supply pipe and the return pipe. The pipes have been fitted with thermal flow balancers so that we can see the direction of flow. When the flow starts, the spring extends. The crossover bridge also has a thermal flow balancer. Our secondary circuit starts at the bridge, runs through a small secondary pump, and back to the bridge. The common pipe is this thermal flow balancer, which has been equipped with 2 springs instead of 1, so it can show flow in either direction. With the secondary pump off, let's start the primary pump. Notice that flow starts in the primary circuit and in a forward direction across the bridge. But there's no flow in the secondary circuit, just as we had predicted. If we want flow in the secondary circuit, we can simply turn on the secondary pump. And we see flow in the secondary circuit. And we should see reverse flow in the common. That's because the secondary flow rate is greater than the primary flow rate. So the difference must be made up by recirculating secondary flow backward through the common. We can adjust the secondary flow by adjusting the valve on the thermal flow balancer in the secondary. If we add just enough resistance, we can reduce the secondary flow to equal the primary flow. We'll know that the two are equal when there is no flow in the common. If we continue to reduce flow in the secondary, we should see a change to forward flow in the common. I hope this demonstration has been useful to you in understanding the terminology used in primary-secondary pumping. How primary-secondary